All right, so we are going to take a look at basic chemistry. So we'll start out with the most basic parts. So this is our basic chemistry, our second lecture. So now we're going to take a closer look at atoms specifically here. We're going to look at the different structures of atoms, and then we'll look at how they interact. So first of all, what is matter? Matter is any material that takes up space. And so we'll be taking a closer look at different types of matter, so the different materials that take up space. And so while we're doing this, what we're going to be doing is looking at it in the way that it's been broken down in chemistry already, and that's by looking at the different elements. Perhaps you're familiar with the periodic table of elements. This shows all of the different types of elements, which are the different types of atoms that are on Earth. And many of these are necessary specifically for living organisms, meaning that they need to be inside of the living organism, meaning the animal or the bacteria or the algae or whatever it is. But all of them are required for life on this planet. So our elements are pure substances, or a pure substance that cannot be broken down by chemical means into other substances. So this means that when we're talking about an element, so carbon, for example, when we're talking about carbon, if we take something, any type of tool, and break it down into something smaller, we still have pieces of carbon. We cannot break these elements into anything smaller. So if we're talking about, say, carbon dioxide, for example, so carbon dioxide, this is not an element. Carbon dioxide is a molecule because it's composed of carbon and 2 molecules of oxygen. So in this case, we can split these apart. We can break them down into other substances, into carbon and oxygen, for example. But when we get to the carbon, we are unable to break that down further. And so then we have our periodic table of elements, which is telling us all of the different elements. And again, these elements cannot be broken down any further. And what is making up these elements are the atom. So I'll write that up here. So the atom is the smallest bits of matter, the smallest bit of matter. And then these atoms are making up the elements. So we can have an atom of carbon, for example, or an atom of hydrogen. And so these are the things that cannot be broken down into any other substance themselves. So if we take a look at this periodic table of elements, we can see carbon here. We can see hydrogen here, oxygen, and nitrogen. So these that I have just outlined, the carbon, the hydrogen, the oxygen, and the nitrogen, these are called bulk elements. So these are needed in large amounts in life. And by large amounts, what we're talking about, for example, in a human, these 4 elements make up about 96% of a human. So these are what are making up by far the majority of a human organism. So these bulk elements are used for things like carbohydrates, for our different lipids, our proteins. We need these things for DNA and RNA, which are going to transfer our information. So these are the bulk elements, and you should be familiar with these. So when we're talking about our bulk elements, what we're talking about are carbon, hydrogen, oxygen, and nitrogen. Then, if we look a little bit closer at some other ones, and we're going to take a closer look at these when we get to our biological molecules as well. But the next kind of group you should be familiar with are the minerals. And these are kind of our bulk minerals, or things that we need in lesser amounts, of course, than the bulk elements, but still in pretty good quantity. So these are needed in smaller amounts, though. And when we're talking about things that we need in smaller amounts, those are things like calcium, which you can see up here, calcium. Things like phosphorus, sodium, potassium, sulfur, and chlorine. So you can see those up there. You can see our calcium I've already outlined up there, phosphorus over here, sodium back over here on the left, potassium, potassium, sulfur, and chlorine. So these are our minerals that, again, we need in some good quantity, but a lot less than our bulk elements. And then the last group that we will talk about in this class are the trace elements. So these trace elements are needed in even smaller amounts. So these are needed in very small amounts, but are, again, necessary for life. So we're talking about the trace elements, we're talking about things like magnesium, we're talking about things like manganese, iron, copper, zinc, cobalt, fluorine, iodine, and many other things. So those are some of the main ones. All right, so you should be familiar with these three different kind of groups of elements. Mainly, we're going to talk about the bulk elements in this class. We will touch on the minerals as well, and then the trace elements. You should just kind of know that those are things that are necessary for life. So now what I'd like to do is I would like to move on to the structure of an atom. In general, we have the two main parts. So in the center, we have what's called the nucleus. And then outside of the nucleus, we have what's called an electron cloud. Now, when we take a look at these two different parts, we can actually break them down into smaller pieces. So again, the atom is our smallest bit of matter. What takes up space. And then we can look even closer. What we're doing here is we're taking a closer look at the structure of this atom itself. And so the nucleus actually contains two different parts. It contains the protons and the neutrons. And then this electron cloud includes the electrons. So what that ends up looking like is we have these little tiny pieces in the center here, which would be the protons. And then we have our neutrons as part of the center here as well, as part of the nucleus. And then flying around the nucleus, we have electrons. Now, the number of protons and the number of neutrons that I have drawn here is just for illustration purposes. So we have our protons, we have our neutrons, and we have our electrons. Now our protons have a positive charge, so they're positively charged. Our neutrons have no charge, and our electrons have a negative charge. And so what we have in the center here, in the nucleus, we have our positive charge and our neutral charge, and then flying around the nucleus, we have our negative charge. So let's take a closer look at each of these different pieces of the atom. So first we'll start with our protons. So remember, the protons are our positively charged piece of the atom. That can be shortened as this kind of lowercase cursive p with a plus sign above it. So our protons are positive charge, and they are what are going to determine the identity of the atom. So meaning it's going to determine what element it is. So the number of protons then, so the number of protons is going to equal the element. And when we say that that equals the element, what we're actually talking about is the atomic number. So if we take a look at the periodic table again, I'll just draw one of these kind of rectangles of the periodic table. Let's say carbon. So the abbreviated form for carbon, the symbol for carbon is the C here. I'll just write carbon at the bottom so we remember. What we'll see in the periodic table is we'll see a number up at the top, and then we'll see a number at the bottom. I'm shortening this number. It has this little bit. I guess I'm not shortening it, but so this would be a box on the periodic table of elements. And so if we look at this right here, this is our symbol. So our C, our uppercase C, is for carbon. And then up here, this is our atomic number. And so for carbon, carbon has an atomic number of 6. What that means then, if our atomic number is 6, then that means that's the number of protons we have in the nucleus. So that means that we have 6 protons in the nucleus. Oops, don't need that last one. So we have 6 protons in the nucleus, and that gives us our atomic number. So if you're given the atomic number of anything, you can just look on the periodic table of elements and you can determine the element. So if we see that the atomic number is 6, we can look on the periodic table of elements and we see that 6 gives us carbon. If we look on the periodic table of elements and someone tells us that there are 17 protons, then we can look on the table and we can see, actually we can go up here and we can take a look. So let's see if we go to the periodic table of elements and we say, okay, 17 protons. If we have 17 protons, if we look along here, they're in order here, so it should be pretty easy. So we start up here with 1. Hydrogen has atomic number of 1. Helium 2. Then we come over here, lithium 3, beryllium 4, and we go down these rows. So if we say 17 protons, what does that give us? 17 protons, our atomic number is 17, then that means we're talking about chlorine here. Now if we say 8 protons, what if we say 8 protons? What element are we talking about? Right, we're talking about oxygen here. So our number of protons is the atomic number, and you can see in a lot of the periodic table of elements, they actually show you the atomic numbers up here in the upper left-hand corner. So if you look at the periodic table of elements, then you can note that if we change the number of protons, or if we change the atomic number, then we're changing the element. So if we say we have an atomic number of 6, or if we have 6 protons, then we're talking about carbon. But then if we say, what if we add another proton? If we add another proton, then we're talking about 7 protons. And if we're talking about 7 protons, then we're not talking about carbon anymore. Then we would be moving up to nitrogen, for example. So another example, if we saw helium, when we saw helium, the abbreviation or the symbol for helium is He. Up at the top, it has a 2. At the bottom, 4.003. So here, again, is our atomic number, 2. That means that it has 2 protons in the nucleus. Now, if we move on to our neutrons, so those are our protons, so we're going to put this all together in a moment here. So our protons, then we have our neutrons, which remember our neutrons gave us neutral. So the kind of shorthand that we use for neutrons is a little cursive N with a 0, meaning 0 charge. So our neutrons are going to determine the weight of the atoms. So in this case, rather than it being the atomic number, then what we're talking about is the atomic weight, or also called atomic mass on the periodic table of elements. So if we recall what we had already talked about, we had talked about how we have the protons and the neutrons are part of the nucleus. So then if we look at something like carbon, for example, and we take a look at the box here from the periodic table. So we already said the atomic number is going to give us the number of protons, and that's going to be 6. Now down here, this is our atomic mass, or atomic weight. And so we can kind of round it for a moment and say that that's 12. So if our atomic weight or atomic mass is 12, then that means that 12 is going to equal the number of protons plus the number of neutrons. Now, if we already know that it's 12, right, and we know the number of protons, what's the number of protons? Right, 6. Then we can figure out the number of neutrons, right? Because if we have this, then all we have to do is we take our 12 and subtract the 6 protons, and that's going to give us the number of neutrons, which means that we get 6 neutrons. So our atomic weight or atomic mass is going to be determined based on the number of neutrons in the nucleus. So then if we look up here, we had our protons, so now we can add 1, 2, 3, 4, 5, 6 neutrons to our nucleus. So we have 6 protons and 6 neutrons. And then that gives us our atomic mass of 12. Another example, if we took sodium, for example, sodium is Na. And if we looked at that, we would see that we have an atomic number of 11. Atomic number is 11. And then for sodium, we have our atomic mass of 23. So if we did the math on that, we have our atomic mass of 23 is going to equal, again, the number of protons, right, which is 11 because we have our atomic number, plus the number of neutrons. So then if we take our 23 minus 11, then we get 12, right? I can do that in green. So we have 12 neutrons. So that's how we are going to be able to determine the either atomic mass if we don't have it. If we're given the protons and the neutrons, we can figure out the atomic mass. If we're given the atomic mass and the atomic number, then we can figure out the number of neutrons. If we're given the atomic mass and the number of neutrons, we can figure out the number of protons, which would be the atomic number. So we can manipulate those three numbers any way we would like. So number of protons plus neutrons equals atomic mass. So then our last piece, so we've talked about the protons, we've talked about the neutrons, now let's talk about our electrons. So we already mentioned our electrons are negatively charged, that's a little E with a negative sign. So our electrons are negatively charged, and these are the pieces of the atom that are going to interact with other atoms. So these are going to form bonds and hold molecules together. So in a neutral atom, so one without a charge, so in a neutral atom, then we have the number of electrons is going to equal the number of protons. So when we are given the atomic number, remember the atomic number gives us the number of protons, then we can say that if we're given the number of protons, then we know the number of electrons because it's not interacting right now. It's not an ion. It doesn't have a charge. It's a neutral atom. So if we're given the atom, we can look on the periodic table of elements and we get the number of electrons. So our examples up here, if we see our examples of our carbon, right, we have 6 protons, right, so we have 6 protons in carbon. Then we know, because we're given the atomic mass, 12 minus 6 means that we have 6 neutrons in the nucleus. Remember, these both are in, the nucleus. Then since we have our 6 protons, we also know that we have 6 electrons floating around in the electron cloud. Down here, we could say for helium, for example, and then we can add our drawing here. So we can have 1, 2, 3, 4, 5, 6 electrons floating around in the electron cloud. For helium here, we can add our neutrons, and then we can add our electrons here, which would be 2. And we know that it's 2 because our atomic number, which is the number of protons in our neutral atom, is going to equal the number of electrons, which is 2. So for example, in hydrogen, if we look at the periodic table of elements, we have 1 proton, and then we have 1 electron. So we just kind of look at the periodic table elements here. Again, here's hydrogen, 1 proton, 1 electron. Carbon, 6 protons, 6 electrons. Oxygen, 8 protons, 8 electrons, and on and on. So these are our neutral atoms, and that's where we're going to start, is with neutral atoms, and then we're going to talk about how that can change when we talk about bonding. So one thing I do want to talk about is related to the fact that when we saw that kind of rectangle from the periodic table, and we saw carbon had 6 atomic number, and then down here is 12.011. Now I just jumped to or rounded down to 12, and there's a reason that it's not just 12 and that it's actually 12.011, and that's because of something called an isotope, or some things called isotopes. Now an isotope is an atom with the same number of protons but with a different number of neutrons. So we had already said in this regular carbon, neutral carbon, we had 6 protons, 6 neutrons, and that gives us an atomic weight of 12. Now, we actually have different isotopes. And so isotopes, again, they have the same number of protons, so our atomic number stays the same. It's always going to be 6, and 6 is going to be carbon. But we can change the number of neutrons, and that produces a different isotope. So it doesn't change the type of the element. It's still carbon, but it will change its behavior. So in our regular carbon that we've been talking about, we had our 6 protons, right? So 6 protons, and then we had our 6 neutrons. And then on the outside here, we have our 6 electrons. Now when we're talking about an isotope, the thing that is going to change in an isotope is going to be the neutrons. So if we have an isotope of carbon, we still have our 6 protons, but we can have a situation where we have 7 neutrons. So if we have our 6 protons in the middle, then we have our 7 neutrons in the nucleus. Then what we have, in this case, this is just carbon, right? This is what we've been talking about is carbon, 6 and 6 and 6. Over here, what we have is called carbon-13. So in this case, then we still have our electrons flying around here. Our 6 electrons. So we have a different number of neutrons, and that's what's changed in the isotope, and it gives it just different properties. But then what we see is that we have a different atomic weight here. So in this case, our atomic weight or atomic mass would be 12. In this case, our atomic weight or atomic mass is going to be 13. That's why it's called carbon-13. Then we also have another isotope of carbon that has, again, it has 6 protons because that doesn't change. That means that it's carbon, but it has 8 neutrons. And then, of course, we still have our 6 electrons. So our 6 protons, 1, 2, 3, 4, 5, 6, 7, 8 neutrons. And we'll put the electrons out here, just to be clear. And then in this case, we have our 6 plus 8. This isotope is called carbon-14. Perhaps you've heard of carbon-14 because this is used in carbon dating. And then in this case, if we add up our 6 protons plus our 8 neutrons, then we get a nuclear mass or nuclear weight or atomic mass, atomic weight of 14. So we have 12, 13, and 14, and these are all different isotopes of carbon. Now the reason that we have our 12.011 is because the atomic weight or the atomic mass that's placed on a periodic table of elements takes into consideration the other isotopes. So it's not just the simple carbon-12, which is what we see mostly in the environment and mostly in living organisms, but we do see carbon-13 and we do see carbon-14. Now, there's not much carbon-13 and not much carbon-14. And so what they take is the amount of carbon-13, the amount of carbon-14, and the amount of carbon-12, and it's all kind of manipulated numerically to give us an atomic weight that is slightly above 12, taking into consideration how much of each of these isotopes there are. So you can see how close it is to 12 tells us that there's a lot more carbon-12 than the other isotopes. So many isotopes are unstable or are radioactive. So what that means then is that they are going to be releasing energy to become more stable. So we have radioactive or unstable isotopes. So for example, we have our carbon-14, which is unstable, which we just talked about. We use the radioactive properties of that. We have phosphorus-32, we have hydrogen-3, and many other types. So these are going to be releasing energy to become stable. So they want to be stabilized. They want to get to a nice stable location, so they're releasing energy, releasing energy, releasing energy. As they're doing that, we have something that we call a half-life. So a half-life is the time that it takes for half of the sample to decay. So half of the sample to be releasing its energy to try to get to stability. So time it takes for half of the sample to decay is what it's called. So the reason that these radioactive isotopes or unstable isotopes are mentioned is because they can be very useful. They can be used for cleaning different things. They can be used for radiation therapy. That's what we're doing when people undergo chemotherapy, for example. They'll have radiation therapy. They can be used for different diagnoses. They can be used for x-rays. We use them for x-rays, for various types of research. So these radioactive or unstable isotopes are helpful. So as you may already know, we have carbon-14 is used for carbon dating. However, they can be dangerous. So they can be useful and they can be dangerous. And so you can actually get burns from these radioactive or unstable isotopes. They can actually damage the cells and they can cause cancer. So you can actually get cancer from radiation therapy, but we also kill cells utilizing radiation therapy. So that is a side note. Let's get back to kind of the structure of our atom. So we talked about the different isotopes, and we've talked about our protons, we've talked about neutrons, we've talked about electrons. Let's take a closer look at the electrons, because we've taken a closer look at the protons and the neutrons in the nucleus. We've said that the protons are positively charged, the neutrons are neutral in charge, and they make up the nucleus. So they're all stuck together in the middle of the nucleus. And thus far, I've been drawing the electrons in their electron clouds without kind of telling you why I've been drawing them the way I have. So let's take a look at why that is drawn that way. So when we talk about electrons, they exist in these paths or these shells that are around the nucleus. So electron shells. So we have the nucleus, and I'll just kind of shorten the nucleus as just one little red ball in the center here. So of course that contains both the protons and the neutrons, depending on if it has both protons and neutrons. So we have the nucleus in there, and then again, flying around in the outside, we have this electron cloud. And the reason it's called an electron cloud is because the electrons are flying around very, very fast. They're moving so fast that it's difficult to keep track of them. It's said that you can either stop them or not stop them, but either way, we have this big cloud. They're moving around very, very quickly. But as they're moving around, they are moving around in these different paths, or these different shells that are around the nucleus. And these shells can hold a certain number of electrons, and that's important to know, these different shells and how many electrons they can hold, because that's going to indicate the types of bonds that we can make and the different molecules that we can make. So when we look at the different shells, we have the first shell, and the first shell can hold only 2 electrons. So 2 total electrons. So if we talk about a shell, oftentimes we draw it in this way. So again, the red dot is the nucleus, and then we have the first shell, or the first path around the nucleus, can hold 2 electrons. Then we have our second shell, and our second shell and third shell, and that's as high as we're going to go in this class, really. Maybe the fourth sometimes, but the second and third shell are going to hold a total of 8 electrons. So again, when we have that, we can draw our nucleus, and then we have our first shell. So we always want to fill the first shell first. So we always fill it with our 2 electrons, and then we can draw another ring or another circle around that, and then we're going to fill it with our total of 8 electrons. So it can hold less than 8, just like our first shell can hold less than 2, but the maximum it can hold is 8. So typically it's drawn in groups of 2, as we'll see why that's useful when we do our bonding. So we have 2 in our first shell, and then we have our second shell, which has a total of 1, 2, 3, 4, 5, 6, 7, 8. Then, of course, we can have our third shell. That, of course, requires a first shell that has 2 electrons, because we fill the first shell first. Then we have a second shell, and if we are going to have a third shell, that means that the first shell is filled with electrons, the second shell is filled with electrons, and then now we've gotten to the third shell, and we can have a maximum of 8 electrons in the third shell. So electrons want to fill the inner shells first, and we want to have a full shell of electrons. So if there's a first shell, we want to have 2 in it to be stable. If there's a second shell, that means we will have the first shell full with its 2 electrons. Then the second shell wants to have a total of 8 electrons to be stable. Then we want to have a third shell, so this would total 10 electrons, right? So 8 in the outer shell, and then 10 total. And then in this case, we have 8 in the outer shell, but in this case, we have 18 electrons total, because we have 2, then we have 8, and then 8. So what these atoms always want to do is they always want to have a full outer shell, whatever outer shell that is, whether or not the outer shell is the first shell, whether or not the outermost shell is the second shell, or whether or not the outermost shell is the third shell. They want to have a full shell. So for example, if we talk about carbon, right, we have our nucleus, which, what do we have in the nucleus? Right, our protons and our neutrons. How many protons do we have in there for carbon? Right, 6 protons. How many neutrons? Good, 6 neutrons. How many electrons? Good, 6 electrons, because we're talking about carbon here, right? So let's draw in our shells for our carbon. So we have said now that we have 6 electrons. We start out with our first shell, our first electron shell. If we have 1 shell, right, we have 1, 2 electrons. Now, do we need another shell? Yes, of course, because if we want to get to 6 electrons, 2 isn't going to do it. So we have 1, 2, 3, 4, 5, 6. So that gives us our total of 6 electrons. Now we have our first shell, which is full. And then we have our second shell and it's not full, right? So we're missing electrons here. So we want to have another one here. We want to have another one here. We want to have another one here. And we want to have another one here. So in order to have a full outer shell, we would need to have 4 more electrons. And so then what we see in nature is that carbon, for example, is looking to bond with up to 4 other atoms in order to fill its outer electron shell. And we're going to take a closer look at that when we get to bonding. Before we get to that, let's talk about the noble gases. So the noble gases are atoms that have a stable number of electrons. All right, so stable number of electrons. What does that mean? That means that its outer shell is completely filled. And if its outer shell is completely filled, then it's not looking to fill its outer shell, which means that it doesn't interact. So it doesn't interact with other atoms. So in this case, if we have a completely full outer shell, then it's not going to be interacting. Out there in nature, it's not going to be trying to grab onto other electrons, it's not going to be trying to get rid of electrons, and it's not going to be trying to share any electrons. It's just out there all by itself. And again, we don't see that with carbon, for example, which is why it's such an important element in nature, in life, is because it is able to interact with things and make up molecules. So let's take a moment to talk about ions. Thus far, what we've been talking about are the number of protons equaling the number of electrons, and that gave us a neutral atom. Now let's talk about when that isn't the case, when we don't have a neutral atom. When we don't have a neutral atom, what we get are called ions. So ions are atoms that take or give up an electron. So atoms that take or give up an electron to get a full shell. So again, we want that outer shell to be full, so that atom is going to be seeking out ways to have a full outer shell. And the way that that can happen is they can either get rid of electrons to make a full outer shell, or they can gain electrons to make a full outer shell. So what this does then is it changes the charge on the atoms. And we'll take a closer look at that. So if we have only a few electrons in the outer shell, the atoms are going to give up their electrons. So they're going to get rid of them. And then that's going to cause a change in the charge. If the outer shell is almost full and we're just missing, say, 1 electron or 2 electrons, then it might take electrons from somewhere else, and then that's going to change the charge as well. So let's take a look at some examples of that. So if we have sodium, sodium has 11 protons and 11 electrons. So if we draw our sodium, right? So I'm not going to draw 11 protons in here. That's just going to be our nucleus there. Let's, however, draw in our electrons. So again, we have our first shell. You should be able to draw these on your own. So our first shell has 2. Then we can draw in our second shell. So if we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we want to get to 11, right? So if we're at 10, we need to have another shell. So we're going to take and we're going to add a third electron shell, and we're going to put 1 electron in it. So in this case, remember, our atoms want to be stable, meaning they want to have full outer shells. In this case, we are missing 1 here, we're missing 1, 2 here, we're missing 1, 2 here, and 2 here. So we're missing a whole lot of electrons in this outer shell, but sodium wants to be stable. It wants to have a full outer shell. So would it, do you think, be easier for it to gain 7 electrons, so somehow get 7 electrons from the environment, or do you think it would be easier for it to just give up a single electron. Right, it's going to be easier for it to just get rid of one. And then if it gets rid of one, then what we see is we can get rid of this entire outer region here, right? So we can get rid of this entire outer shell. It's going to get rid of that electron. And since it got rid of the electron, now it has a full or stable outer shell. Now when it does that, again, when we started out, we had 11 protons and 11 electrons, which meant that we had no charge. The number of pluses, or positiveness, in the atom equaled the amount of negativeness, right? The positives and the negatives equal out, giving us 0. But now, we still have our 11 protons because our nucleus doesn't change. But in this case, now we only have 10 electrons. So in this case, now we have lost this single electron. It's out there somewhere in the environment. We only have 10 electrons. What does that give us now? That gives us 1 positive charge, doesn't it? And so what that means is that once sodium releases that electron to the environment, then it's going to become a positive ion. So we have more positive pieces than we have negative pieces, right? And so we have a positive ion, and a positive ion is called a cation. I try to remember that because I like cats. So positive, I like it. Cation, I like cats. A positive cation. So we have a cation is sodium because it gets rid of that negative electron. So now we have 11 protons, 10 electrons, which means we have more positive in this atom than we have negative. And that would be written then as sodium plus 1. Now if we look at another example, oops, that's not what I wanted to do. If we look at another example, let's say our chlorine atom. So if we look at our chlorine atom, we actually have 17 protons, which means that we would have 17 electrons. So then if we draw this, again, I'm just going to draw this as our nucleus here, which includes our 17 protons. Now let's draw in our electrons, and again, you should be able to do this. So our first shell, 1, 2. Second shell, 1, 2, 3, 4, 5, 6, 7, 8, right? So that gives us 10 total, but we need to get up to 17. So we need to add another shell, don't we? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So there's our 17 electrons, which, do we have a stable outer shell? No, because we're missing 1 electron there to give us our 8 total in the third electron shell, because we want to have a stable outer shell. So in this case, when we're talking about our chlorine, in this case we can either get rid of the 7 electrons we have in the outer shell, get those to go somewhere else, or we can gain a single electron. What do you think would be easier? Right, we're going to gain a single electron. So our chlorine atom is going to grab onto another electron. So in this case, again, we're still going to have our 17 protons. But then now we're going to grab an electron and we're going to add that here. So now instead of 17 electrons, how many electrons do we have? Right, we have 18 electrons. So now we no longer have this, the same number of positive and the same number of negative, which means we're going to have a difference in charge. So what is our difference in charge here? Right, 1 electron difference. So now in this case we have more negative charge than we have positive charge. We are stable now, we have that stable outer ring or outer shell, but now what we have is a negative ion. And a negative ion is called an anion. So an anion is a negative ion. So in this case, we would write it as Cl minus because we have one negative charge. So in both of these cases, so in the sodium, we got rid of an electron, gave us a positive charge. In chlorine, we gained an electron, gave us a negative charge. We can do this with more than that too. For example, magnesium. Magnesium, if you want to draw that out, is going to give up 2 electrons. So then it's going to be 2 plus. On the other hand, oxygen gains 2 electrons. So this would be 2 minus. And so they are going to be drawn respective of the number of electrons they give up or the number of electrons that they gain. And so that's how we have our different types of ions. We have our cation and our anions because they're going to be either getting rid of electrons to make a stable outer shell, or they're going to be gaining electrons to make a stable outer shell. So this kind of sums up our general structure of the atom. You should be familiar with all of the different parts and pieces, the isotopes, the ions, and I recommend practicing figuring out the atomic weight, figuring out, or given the atomic weight, figuring out the number of protons, figuring out the number of neutrons, the number of electrons, knowing the different isotopes, and then also understanding and being able to draw out the electron shells, knowing that the first electron shell has 2, subsequent ones, the second and third shell have 8 total in each, and that our atoms want to have a stable outer shell.